So welcome back to part 3 of lecture 8. So what we're going to do in this part is kind of prove some things about dimension, about what happens when you take two subspaces and you add them together. So here's the statement. Let's say we have two subspaces, U1 and U2 inside of V of a finite dimensional vector space. And then we're going to take the sum of those two subspaces. And the question is, how big should that new subspace be? Can you determine that information from the two subspaces you started with? And there happens to be a formula in this case. It should be the dimension of U1 plus the dimension of U2, but you need to subtract how big the dimension of the overlap is, okay? So the intersection of the two spaces. So if you're familiar with the principle of inclusion-exclusion, this formula is very similar to that idea. Now, I'm not going to go through all the ideas because it involves checking a bunch of things about whether you have a basis, but I'll give you the main ideas of the proof about how it works. And it uses some of the ideas that we had from last class or last lecture about taking a set of linear independent vectors and expanding it out to a basis of a bigger set. So the main idea goes as follows. We take M to be the dimension of the intersection of these two spaces. So where these two spaces intersect. So you know that this is a finite dimensional vector space, so we know that U1 intersect U2 is equal to the span of a collection of vectors, U1 through UM. So we have that. Now U1 through UM are vectors that are both in U1 and in U2. So what we can do is we can extend U1 up to UM to a basis of U1 and U2. Okay, so i.e., what you get is you should think of U1, and we can take the span of U1 through UM. These are linearly independent vectors inside of U1 because they live inside the intersection. And then we can keep adding new vectors until we've found a basis for U1. This is something we proved in the last lecture. And we can do the same thing for U2. We can take the span of U1 up to UM, and then we can keep adding vectors of U2 that we haven't seen. Let's call them W1 up to WR until we get a spanning set for all of U2. Now, the kind of the technical part that you would have to check is now the following, is you want to claim that if you take all of these vectors here, U1, UM, V1 through VP, and W1 through WR, you want to check that this is a basis for the sum of the two vector spaces. Okay, so it's not actually that hard. You just first check that they're linearly independent, and then you need to check that it's a spanning set. So there's a bunch of technical work to do this, but if you can prove this claim, the rest of the proof follows from the claim. So the result follows from the claim. And let me show you why it follows from the claim. Well, if we're looking for the dimension of U1, U2. Now, if the claim is true, this is my basis, right? And so all bases have the same size. So this tells me that the dimension of this vector space is M plus P plus R, because that's all the vectors that we have. Now, one way we could rewrite this is we can write it as 2M plus P plus R minus M. We're doing kind of our trick of adding in 0 in a special way. Now, when we can break this up a little bit further, and we can say, well, this is M plus P plus M plus R minus M. Now, M plus P is the number of things in my basis for U1, and M plus R is the number of things in my basis for U2. So I have dimension of U1 plus the dimension of U2, and M, right, was, let's scroll back down here, is the number of things that were in my basis for U1 intersect U2. So this part right here is equal to the dimension of U1 intersect U2. So, and that's it. So I'll just let me put here, see the book for the details of the claim. So that's really kind of the only thing that I'm not presenting, but it's something you should be able to read in the textbook and kind of easily follow. Okay? So this gives us a nice way of taking two vector spaces which you know, and then adding them together and get a larger vector space, and you can keep track of the size of the dimension. And as a corollary, what we get is something that's the following. Suppose that we can write V as a direct sum of U and W, then the dimension of V is the sum of the dimension of U plus the dimension of W. Okay, and I can prove the proof and give you the proof very quickly. Remember that V is a direct sum of U and W if and only if V is equal to U plus W and U intersect W only contains the zero element. So we can now apply our previous result, right? So we have that the dimension of V is equal to the dimension of U plus W because of this result. Well, because of our last result, this is equal to the dimension of U plus the dimension of W minus the dimension of U intersect W. But this part here is zero because it's the intersection is zero. So we get the dimension of U plus the dimension of W. Okay, so this is a nice result. These two results are a nice result, kind of showing you some of the things that we've learned about extending bases and keeping track of the size, and then we can compute the dimension. So in the last part of our lecture, I want to do a kind of a more complicated example. So I'll see you in a couple minutes.